2. Where novelty actually resides, the honest novelty in this work clusters in 3 distinct places, each sufficient for a different kind of publication. Point 2.1 The delay line adjacent read bug. And it's where novelty actually resides, the honest novelty in this work clusters in 3 distinct places, each sufficient for a different kind of publication. Point 2.1 The delay line adjacent read bug. And its analysis, the discovery that buff bis 1% n instead of buff bis plus 1% n transforms the KS 2-point average into a comb filter, with the complete mathematical characterization of that transformation, is the most self-contained and cleanest contribution. The analysis deriving h broken e cap j omega equals cos omega n1 2 from first principles and showing why the comb filter fails to suppress Nyquist rate oscillation is technically correct, elegant, and verifiable against spectral measurements. 88% HF content before fix, 1% after fix at MIDI 41. What is publishable here? A short technical note. Note or systems demonstration at ICMC, International Computer Music Conference, or DAFC's Digital Audio Effects. The format is, here is the bug, here is what it actually implements, here is the spectral evidence, here is the one-line fix, here is what implementers of Karplus-Strong synthesis need to check for. Such notes are explicitly welcomed at both venues. The contribution is small in scope, but complete and correct, which is exactly what a short note paper needs to be. Why it matters beyond this project. Karplus-Strong is widely implemented in open-source synthesizers, game audio engines, Max MSP externals, and teaching code. The ring buffer indexing bug has a plausible failure mode. It produces output, it runs without crashing. And without a spectral regression test, it will pass a listening test if one happens not to notice the persistent HF artifact. A documented, analyzed, verified fix with reproducible spectral evidence is useful to anyone implementing KS. CNN14. As a register bias piano evaluator, this is the more substantial and arguably more original contribution. The work demonstrates empirically that CNN14P piano varies by 2 to 3 orders of magnitude across the piano keyboard for the same synthesizer. 0.38 at MIDI 33-241, 0.018 at MIDI 60, 0.003 at MIDI 72. It then shows that this register sensitivity creates a methodological trap. An acceptance test can be redesigned to score above threshold by moving to the register where the evaluator happens to score high. Without any improvement in the synthesizer's performance in the register that matters for the intended musical use, this is the early form of an evaluator validity argument. The claim needs development. The current evidence is empirical rather than a formal validity study. And a formal study would require controlling for the KS filter's own register-dependent spectral slope and comparing against a perceptual baseline. MUSHRA listening panel or established instrument recognition work by e.g. Lawsert 2009-2010 on instrument perception. But the direction is clear. The question it raises is whether pre-trained interclass probe evaluation is suitable as an acceptance gate for synthesizer development at all. And if not, what replaces it? What is publishable here? The register sensitivity, finding the honest critique of test design methodology. This belongs at ISMIR, International Society for Music Information Retrieval, or at the ISMIR late-breaking demo track. ISMIR's audience includes AMT researchers and audio ML practitioners who are actively using PANs as evaluation oracles, a paper titled something like Register-Dependent Scoring in Pre-Trained Audio Classifiers. A threat to instrument synthesis evaluation addresses a methodology gap that ISMIR reviewers recognize. The Death Angel context is the motivational story, but not the scholarly contribution. The contribution is the validity problem, why it matters beyond this project. Pre-trained audio classifiers are being used as automated evaluation metrics across the music generation field. For text-to-music, Music.ly, FAD, FD, for audio quality, FAD, for instrument identification, PANs as feature extractors, and for synthesizer acceptance. None of these uses examines whether the classifier is register neutral, tempo neutral, or loudness neutral. If a piano score of 0.54 can be obtained by changing the test register from MIDI 60 to 72 to MIDI 33 to 40 without changing the synthesizer, then piano is not a reliable single-number piano quality score. Every paper that uses PANs or similar networks as a synthesizer or generation quality metric inherits this vulnerability. Naming it and characterizing it is academically important. The Jaffe-Smith integrated system in a live streaming context. The piano stream system integrates all 4 Jaffe-Smith extensions: B1 dynamics low pass, B2 hammer position comb, B3 multi-string unison beating, B4 tuning Alpus, plus the HS first order in harmonicity filter, and the Freiberg KTH phrase arch velocity model into a single real-time performing system that streams infinite piano music. Each component individually is documented in the literature. The particular combination and its implementation as a single coherent system for live streaming, with the velocity model grounded in a 2023 empirical validation study, Jones and Freiberg 2023, is original. The CA as controller net oracle design, ADR, U0003, is also worth a systems paper at its own right. The decision to use Rule 30 not as a compositional oracle that generates notes, but as a rhythmic gate that controls the probability and timing of note events, with the note selection handled by rule-based voice leading, is a specific architectural choice that has implications for what the system can and cannot do. Bereston and Edmonds' 2005 document The Historical Problem of CA Producing Unmusical Patterns, used directly as compositional output, ADR, U0003, explicitly addresses this by separating the CA's role, gating from the role that generates musical content, voice leading. Wolfram 2002's computational irreducibility argument provides a theoretical basis for why a CA gate is musically interesting, even when the CA itself is not read as a score. The gate's output is contingent in ways that a random number generator is not, but it is constrained in ways that produce meaningful rhythmic structures. What is publishable here? A Systems and Architecture paper describing piano streams design decisions and their musical consequences. 9. New interfaces for musical expression, or ICMC, International Computer Music Conference, would be appropriate venues. The submission type would be concert system or paper, depending on whether the musical output is considered the primary contribution. If you can demonstrate that the live stream produces musically coherent output over extended periods, and that the CA gate produces recognizable rhythmic character that a human listener can perceive as intentional rather than random. That is a 9 Quality Systems paper. Why it matters beyond this project. Rule-based, physically grounded synthesis combined with algorithmic composition is an aesthetic choice that has a small but committed audience in computer music, and the field has moved almost entirely toward deep learning methods. A well-documented, live-performing, rule-based system that produces extended musical output is a counterpoint to the dominant deep learning paradigm. And 9 in particular value systems that demonstrate novel aesthetic position as much as technical novelty. Whether this is novel in the deep learning sense, new architecture, new result, is debatable. It is novel in the sense of a complete working system with a coherent philosophical position that has not been assembled in exactly this configuration before. 3. Where the Death Angel integration adds significance, the Death Angel project is the motivational context for the synthesizer, and it adds a type of significance that academic papers do not typically capture on their own. The system has a specific, named, intended musical use. This matters in 3 ways. An infinite procedural piano stream is not a solved problema system that streams procedurally generated piano music indefinitely, with expressively shaped velocity, physically plausible synthesis. And CA-determined rhythmic structure is not a solved problem in computer music. There are piano synthesizers, many varying widely in quality, and there are procedural composition systems that produce infinite streams, less common, but a system that combines both with a specific aesthetic goal. Here, trans breakdown contrast and actually ships as a live stream is rare. The produces music that a person wants to listen to while working bar is an aesthetic criterion, not an academic one, but it is not a soft criterion. It is the criterion that separates computer music research from art, that nobody listens to on purpose. 3.2's hybrid rule-based plus neural trajectory is positioned for real work. The 2026 Ren-Con results, Zhang et al., Eisner 2026, placed the rule-based director musicist system at first in the preliminaries and second in the final of the expressive performance rendering competition against neural approaches. This is empirical validation that the rule-based performance rendering approach piano stream uses is competitive with the deep learning approaches that dominate the field. The AMD, Audio LDM2, approach, Suno, Udio, and similar text-to-music systems operate at the audio level and produce complete songs. They do not produce infinite streams. They do not have real-time expressive control, and they are not controllable at the level of phrase-level musical structure. Piano stream sits at a different point in the design space, closer to a live instrument than an audio generation model, and that is a defensible aesthetic and engineering choice. The Ren-Con result is recent enough, July 2026, that a paper situating piano stream in this landscape can draw on it directly. 3.3. The system has a clear integration path. The Death Angel integration report documents a concrete, specific integration roadmap with a parallel project, Transstream, that is also a working system. This is distinct from the typical academic project that ends with future work. Evaluate against real data. Here the real data requirement is, ship the synthesizer, run it for a week, observe whether listeners in the intended use context, a person working while the stream plays, notice the treble register deficit. The integration report is honest about the deficit. Piano equals 0.003 at MIDI 60 to 72 is pluck string territory. And if the best register only approach is taken, the musical argument for using a piano synthesizer at all in the breakdown needs to be made explicitly. Does the best register KS piano serve the intended timbral contrast, or does it undermine it? Four. Where the PhD work is, or could Bethis, is the most open and most significant question. A PhD thesis in this area needs to be framed as a coherent research program with a central technical contribution, a methodological contribution, and an evaluative contribution, not as a series of interesting but disconnected findings. The strands assembled in this topic can be made coherent, but the coherence needs to be constructed deliberately rather than assumed. 4.1. What makes this PhD-ready territory physics-based instrument synthesis is a domain with a long tradition. Specific foundational literature, the Jaffe-Smith papers, the Raw-Halov-Alimaki papers, the Valimaki et al. 2006 survey, the Smith and Van Duyn commuted synthesis work, open technical problems, stiff string modeling, sympathetic resonance, hammer scattering, longitudinal vibrations, and a community that publishes at the highest quality venues, ICMC, DAFS. G's, Journal of the Audio Engineering Society. It also has a useful property. Success criteria are partly technical, spectral accuracy, pitch accuracy, stability, and partly perceptual, recognizable as the intended instrument, which means a PhD thesis can make both an engineering contribution and a methodological contribution to how instrument identity is evaluated. The combination of physically grounded synthesis with algorithmic composition has an additional virtue that is underappreciated in academic evaluation. It is the design philosophy that the computer music community historically considered the correct approach to digital instrument design, before deep learning displaced it. Matthews. 1963, The Origin of Computer Music at Bell Labs, the IRCOM Phone papers, the early Stanford CCR MA work, all were physical modeling, not neural. There is scholarly value in a careful, rigorous, physically accurate implementation of piano synthesis for algorithmic composition, even if the market has moved on, because the deep learning approaches being used today are opaque and untrustworthy as musical instruments. You cannot hear the design decisions, and you cannot modify one specific acoustic property without retraining from scratch. A physically grounded system has a transparency and a controllability that neural approaches do not. (4.2) The thesis that is implicit in this work, a defensible PhD thesis framing, is working title: Physically Grounded Procedural Instrument Synthesis for Algorithmic Composition, Design, Validation, and the Evaluation Problem in Neural Audio. Oracle's central claim. Physically grounded synthesis produces instrument-identifiable output that is transparently improvable. Neural pre-trained audio classifiers are unsuitable as acceptance criteria for synthesizer development because their scoring behavior varies systematically with acoustic features, register, loudness, tempo, in ways that do not correspond to perceptual instrument identity structure. Chapter 1. Motivation. Death Angel context framed as a design brief, a practical named use case that requires a synthesizer identifiable as a piano in specific musical registers, streaming procedurally indefinitely. Chapter 2. Physical Modeling Foundations. Jaffe Smith, Karplis Strong, Rahalo Valimaki, Conklin, building the physical basis for the synthesizer. This chapter establishes what physically grounded synthesis can and cannot produce. Chapter 3. The Piano Stream Synthesizer. Complete technical description, architecture, all implemented extensions, HS filter derivation, and implementation. The subdivision of roles between CA gate and voice leading and synthesizer. Chapter 4. Evaluation methodology. The CNN14 register sensitivity investigation. Empirical register sweep, formal analysis of what piano actually measures and measures agreement with audio sets labeled training distribution, not perceptual piano identity. The demonstration that a register stratified test reveals the operative mechanism, KS averaging filter geometry, and the test design hygiene argument. A valid acceptance test for a synthesizer must be register stratified when the synthesizer is register dependent. Chapter 5. Live system and musical output. The streaming implementation, the CA architecture, the Freiberg velocity model grounded in empirical performance data, and a set of documented musical outputs. At minimum, the 16-bar nocturne with measurable piano profiles across registers, and evidence of sustained musical coherence over extended streaming periods. Chapter 6. Discussion. What physically grounded synthesis contributes that neural approaches do not. Transparency, controllability, tractable acoustic analysis, the ability to fix one problem without side effects. The complementary limitations. Physical modeling cannot produce timbres that are not in its parameter space. There are things neural approaches can do that physical approaches cannot. The methodological finding that the field's adoption of pre-trained neural classifiers as evaluation oracles requires a validity argument that has not been conducted. Chapter 7. Implications and open problems. Chapter 7. Implications and open problems. Institutional fit. This framing works at a computer music focus program, ID, at a music technology department, and also at a general electrical engineering or signal processing program, because the methodological contribution, the evaluator validity argument, is engineering quality and independently publishable. The South African research landscape has relevant supervisors had UCT and WITS in music technology. And the UNISA proposal thread is a different track entirely, AAC for post-stroke aphasia. If the UNISA route is the PhD, this work needs to be positioned as exploratory pilot for the methodology questions that thesis will address. If a computer music PhD is the actual goal, this topic has the content for it, the honest version of the PhD case. A thesis built from this work would pass on the strength of its methodology contribution, the CNN14 validity argument, even if the piano stream synthesizer's treble register deficit remained open at submission time. An honest thesis says, I built a system, I evaluated it rigorously, I discovered that the evaluation method was flawed, I demonstrated why, and I propose a corrected evaluation framework. That is a complete and defensible thesis. It does not require the synthesizer to be perfect semicolon. It requires the methodology to be sound, and the argument to be honest. Users Johannes Code Personal Brainstorm Topics Music Generation. Notes 4.3. What the PhD would need that this topic does not yet have. A PhD thesis requires a formal pre-registered methodology. This topic has not done pre-registration. The investigation was exploratory by design, that is fine for explorative work, but a thesis contribution chapter needs a pre-registered experimental protocol. The pre-registration would cover the register suite design, the acceptance test redesign process, the spectral measurement methodology, and the planned analysis pipeline. Comparative evaluation against alternative approaches. A formal comparison of KS piano synthesis against at least one alternative approach, commuted synthesis, modal synthesis, or a neural timbre model organized around the same evaluation criteria. This does not require the alternative approach to be implemented. A comparative analysis based on published specifications and the same spectral measurement protocol would be sufficient if the arguments are rigorous. A perceptual validation. Validation component. The CNN14 results need a perceptual anchor, at minimum, a small listening study, even 10 to 15 participants, within subjects MUSHRA are similar to demonstrate that the register sensitivity CNN14 exhibits corresponds to actual perceptual differences in instrument identity. Without this, the evaluator validity argument remains technically plausible but empirically underanchored. Controlled experiment for the CA gate's musical consequence. To claim that Rule 30's specific behavior contributes something musically meaningful beyond randomness, the CA gate's output needs to be measured and compared against a random gate baseline for some objective musical coherence metric, simplest. Interonset interval distribution, event density, phase coherence. These are measurable and do not require human listeners. Literature positioning chapter. The 38-paper library is good, but it maps onto multiple literature domains: physical modeling synthesis, AMT, algorithmic composition, music cognition, performance rendering. A thesis chapter needs a literature review that actively positions the contribution. Not here are 38 papers I read, but here is the specific gap each of these papers defines, and here is how my contribution fills it. This is a different task from annotation and indexing. 5. The publishable paper catalog, ranked by maturity. 5 distinct publishable outputs are present in, are derivable from this work. Ordered by how complete each is today. Paper 1, complete. Ready to write. Carpless strong loop correctness. A filter bug in the 2-point average and its spectral consequences. ICMC are DAFC's short paper. Short, self-contained, technically correct, publishable as is with the existing empirical data. Estimated writing time 2 to 3 days from existing notes. Paper 2, complete literature plus empirical base, needs writing. Register-dependent scoring in pre-trained audio classifiers. A threat to instrument synthesis evaluation. ESMIR are ISMIR LBDD. Empirical data exists, argument exists, literature context exists. RenCon 2025, Chaturvedi 2025 AMT Challenge. Who et al. 2024 on musically informed AMT evaluation. Needs framing as a validity study, a small perceptual component, and more careful positioning against related work, audio set label hierarchy critiques, instrument recognition literature by Lossert, meta-evaluation of FAD style metrics. Estimated writing time 3 to 4 weeks. Paper 3. Complete system, needs a musical argument. Piano stream, a physically grounded, SIA-gated procedural piano synthesizer for infinite live performance. NIME or ICMC, needs documentation of the live system, demo audio or video, a clear statement of the aesthetic position, and evidence of sustained musical output over a meaningful duration. The Deaf Angel integration report provides the motivation. The wiki and KB document the learning trajectory. The synthesizer is functional. What is needed is a demonstration recording and a written argument about what this system offers that other approaches do not. Estimated time 4 to 6 weeks, including a recording session. Paper 4, scoped research project. Inharmonicity implementation in carpless strong synthesis. First order Alpes and phase delay cascade comparison DAFs or Gs. This would be a focused synthesis paper. Both the HS first order implementation and the Rahul of Alimaki-Theron cascade approach are documented and partially implemented. A formal comparison against both a reference, modal synthesis, or real piano recording, and against each other across the keyboard register would constitute a synthesis paper. G specifically values rigorously measured audio quality results with perceptual anchoring. Estimated time 6 to 8 weeks, including implementation, measurement, and a small listening test. Paper 5. PhD thesis program, 2 to 3 year program. Physically grounded procedural synthesis for algorithmic composition with CNN14 validity as the methodological core. See section 4.2 above. 6. The hard questions, answered honestly. 6.1 Is any of this actually novel? The delay line bug discovery is genuinely novel in the sense that the mathematical analysis of what the broken form implements is original and verified. The register sensitivity finding is genuinely novel as a named Characterized methodological problem. And the combination of all 4 Jaffe-Smith extensions with HS in harmonicity in a live streaming system is a novel configuration, even if every component was published individually decades ago. Is this important novelty in the deep learning paper sense, transformer architecture, new benchmark result? No. It is narrower, more domain-specific, and more useful to a smaller community. That is not the same as unimportant. 6.2. Why does piano stream specifically matter? It matters if, and only if it produces music that is worth listening to. The technical quality of the synthesizer is a necessary, but not sufficient condition for that. A synthesizer that scores piano equals 0.003 in its intended register is still producing a recognizable, structured, procedurally infinite stream of piano-shaped sounds. And whether that stream is musically viable depends on whether the compositional layer, CA gate plus voice leading plus velocity model, produces musically coherent output. The Wiki's entire pedagogical project, going from zero knowledge to a working physical modeling synthesizer with an understanding of every architectural decision, is the strongest argument for the system's musical legitimacy. The design decisions are visible, auditable, an improvable A-string of procedurally generated piano, notes with expressive velocity shaping, and a CA-determined rhythmic structure that runs indefinitely as a working instrument, not a research prototype that produces a few seconds of output for a demo. The Death Angel context demands exactly this kind of sustained output, and a system that truly streams piano music while someone works is doing something that 5-minute demo outputs do not do. 6.3. Is the thesis direction viable? Conditionally, yes. It is viable if and only if the methodology contribution, the CNN14 evaluator validity argument, is developed as the primary thesis contribution, with the piano stream synthesizer as the motivational and illustrative system, not as the primary technical result. A thesis that argues I built a piano synthesizer, and here is why that is hard, and here is what I discovered about evaluating it is stronger and more honest than a thesis that argues I built a piano synthesizer, and it sounds like a piano. The latter thesis claim is currently false in the treble register. The former thesis claim is robust and defensible regardless of whether the synthesizer has ever completed the PhD program risk is scope discipline. The topic has sprawled across 10 literature domains, to-live systems, piano stream, and the Death Angel integration, and a pedagogical infrastructure. A PhD thesis needs a sharp, bounded research question. The suggested framing above does that: 1 central system, 1 central methodological contribution, 1 evaluation framework, 1 musical argument. It does not require all 4 Jaffe-Smith extensions to characterize in the thesis. What matters is the 1 extension, HS in harmonicity, that made the register bias visible, the register sweep data, and the argument about evaluation validity. 6.4. When should this work be stopped and reframed? If the honest answer to does this do anything deep learning cannot do better is no, actually not, then the value of the work is not in the synthesizer's acoustic quality, but in the methodology and the pedagogical record. There is no shame in that reframing. The methodology contribution is already in the existing data. The pedagogical record, the wiki, the KB, the annotated paper library, is a real educational accomplishment that documents a genuine learning trajectory. These things are worth preserving and worth publishing on their own terms. Separate from the question of whether piano stream passes as a piano, the worst outcome would be continuing to attempt synthesizer improvements without acknowledging that the treble register problem reflects a fundamental limitation of physical modeling with a one-pole low-pass feedback loop, and that the physical modeling approach may not be what is needed for Death Angel's intended use, which involves MIDI 60 to 84 treble register piano, for which the physics of KS averaging simply cannot produce sufficient spectral darkening regardless of what filters are inserted. If when the dust settles, the right answer to Death Angel's piano breakdown problem is use a sampled piano, that is also a result, and a respectable one. Physically grounded synthesis is not a universal solution, and recognizing its boundaries is part of rigorous engineering. 7. Actionable next steps in priority order. These are the next concrete steps available, ordered by contribution to effort ratio. Step 1. Already planned. Write the formal investigation report notes, July 19, 2026 Pampian investigation, dis already outlined in the report plan file. Completing this is the immediate priority. It is the formal publication-ready document that records the bug discovery, the HS implementation, and the register sensitivity finding with full citations. Estimated effort, 1 to 2 days, writing the 6,000 to 8,000 word document against the existing plan and data. Step 2. Commit the investigation report and generate the planned figures, run the figure generation scripts, verify all 6 figures render, and commit the formal report. This makes the technical contribution packageable as a preprint or conference submission. This is a half-day task. Step 3. Write paper 1, the KS bug note. From existing data, all data exists, all citations are in the bibliography, the mathematical derivation is complete. This paper is ready to draft. Target: ICMC 2027 or DAFX 2027. Submission timeline: Paper 1 draft by end of July 2026. Submit to DAFX 2027. Deadline approximately May 2027. Step 4. Develop the CNN14 validity argument into a methodology paper. Paper 2. This requires adding a perceptual component, even a small listening study. N10 would be meaningful, and framing the argument against the AMT evaluation literature, who et al. 2024 is the natural position. The 2026 RenCon result provides a directly comparable recent example. Rule-based rendering winning against neural approaches, which is precisely the kind of empirical finding that supports the argument that automated neural evaluation is not a valid oracle for musical quality. Estimated 4 to 6 weeks, including the listening study design, execution, and analysis. Target: ISMER 2027, are a methods-oriented journal. Step 5. Produce a demo recording of the piano stream Systema 10-20-minute continuous stream recording, demonstrating the CA-determined rhythmic structure, the phrase-level velocity shaping, and the instrument's sonic character. A recording is necessary for the NIME ICMC Systems paper, Paper 3, and also as a concrete artifact for the PhD thesis. This also provides a direct perceptual answer to does the current system sound good? That no amount of spectral analysis can substitute for. A recording that genuinely sounds like sustained piano music, even with the treble register limitation, is a stronger argument than any amount of piano data. Step 6, longer term. Pre-register the PhD methodology. The PhD program question is the longest horizon item in this list, but it frames everything else. Resolving the thesis framing, specifically whether the primary contribution is the CNN14 evaluator validity argument, strong, defensible, falsifiable, or the physically grounded synthesizer, partial. Technically interesting, but not musically complete in the intended register, determines what paper should be written in what order and what further experiments are needed. The pre-registration step is writing the methodology document that specifies the PhD grade listening study, the formal register stratified acceptance test, and the comparative evaluation framework before further experiments run. This prevents the exploratory pattern from this topic, measure, discover, adjust, measure again, from continuing into the PhD program, where it is not appropriate. Step 7 conditional. Decide on treble register HS, cascade the Rauhalv-Alamaki Theron, all pass cascade. 4 second order biquads in program where it is not appropriate. Step 7 conditional. Decide on treble register HS, cascade the Rauhalv-Alamaki Theron, all pass cascade. 4 second order biquads in bass falling to 1 in treble, with a 1 equals 1D, D plus 1, D equals EXP, CD. B, I key, KDB, is the physics-accurate approach to inharmonicity and is not yet attempted in this implementation. The first order HS is correct and stable, but produces smaller inharmonicity than the Theron cascade would produce at equivalent B values. Whether implementing the full Theron cascade produces perceptible improvement in the treble register is an empirical question that is worth one experiment. Implement it, measure it across the keyboard, and decide from data whether it closes enough of the treble gap to change the musical viability of the approach. This experiment is well scoped, 1 implementation, 1 measurement sweep, 1 decision point, and would close the open question honestly. 8. Editorial statement. The report was written by the researcher who conducted the work. It is not a pitch. The thesis case is presented honestly. The strongest contribution is the methodology argument, not the finished synthesizer. The honest version of the thesis is not "look how far I got that" framing invites rejection on grounds of overclaim. The honest version is I pursued a physically grounded approach to procedural piano synthesis, identified an evaluator validity problem that is independent of my synthesizer's acoustic quality, and propose a corrected methodological framework that the field needs. That thesis will be evaluated on the strength of the validity argument, and on whether the piano stream system is sufficiently functional and documented to serve as the running example throughout the 7 paper sessions documented in this topic, have produced something real and something publishable. The specific publishable units are a short technical note on the KS bug, competitions, ICMC, DAFCS, a methodology paper on CNN 14 register bias, venue, ISMIR, a systems paper on piano stream, venue, NIME or ICMC, and a PhD thesis on physically grounded procedural synthesis with evaluator validity as the methodological core. The right next action is to write the investigation report and the bug note, because those are the items that do not require any further experiments and can become a draft submitted paper. In the immediate term, the most valuable thing this work has produced is not the synthesizer. It is the question, when does a pre-trained neural network's classification of a synthesizer output mean anything about the synthesizer's musical quality? And when does it mean something only about the network's training distribution? That question is interesting, publishable, and worth a PhD. The piano stream system is the case study that makes the question concrete. Plan, real piano reference signature plus 3-way comparison report context. The deeper goal is to establish a persistent, multi-dimensional acoustic signature of a real grand piano that can be used to 1. Understand what the KS synthesizer needs to sound like, the target 2. Decompose the gap into specific tunable dimensions, not just a single P, piano, score, 3. Replace the single metric P, piano, 0.50 acceptance gate with a multi-metric scorecard 4. Track progress over time as KS parameters are tuned to the max Richter departure. Lullaby MIDI plus MP3 is the first reference piece, chosen because it exists and is convenient, not because it is optimal for evaluation. The system must be fully generic. Any MIDI file paired with any reference audio can be used in future work. New pieces will be added to references audio as evaluation needs evolve, e.g., a piece with more bass register coverage, or a solo single-note chromatic scale for spectral analysis. The P, piano, 0.50 gate as previously implemented was inadequate because it was satisfied by choosing a test register that happens to produce a dark spectrum. It doesn't measure anything about the synthesizer's fidelity to a real piano. The signature approach fixes this. Dependency, fluid synth binary is not installed. Install before running. Brew install fluid synth. Deliverables 0. Methodology document file. Topics Music Generation Research Methodology MD. This must be committed before the scripts are run. Pre-registration rule from Doc Standards Research Methodology MD. It is the formal record of what we are building, why, and how it will be used. Sections to include research question. Can the Carplus Strong piano synthesizer be tuned to be acoustically indistinguishable from a real grand piano, as measured by a multi-dimensional reference signature? What is the current gap and which acoustic dimensions contribute most to it? The reference signature framework. Describe the 3-tier evaluation approach. Tier 1, real recording. A real piano recording, MP3/WAVE, rendered from a known MIDI, used as the perceptual and acoustic ground truth. Tier 2, Fluid Synth plus Salamander Grand Piano SF2. A high-quality sound font render of the same MIDI, representing the ceiling achievable with sample-based synthesis. Tier 3, KS Synthesizer, our synthesize note, render of the same MIDI, the subject under evaluation the signature, dependent variable definition. The reference signature is a JSON document extracted from the Tier 1 recording. It encodes the target values for each acoustic dimension. Any synthesizer rendering the same MIDI can be compared to it metric by metric. The signature is not a pass-fail gate, it is a multi-dimensional distance map, showing where the synthesizer is far from and close to the real piano acoustic dimensions, measured, operationalized. Dimension measurement target direction. Piano, CNN 14 pan sigmoid output at class 153 maximes. Real piano spectral centroid frequency weighted mean of Welch PSD. Time averaged match real piano, 2000 Hz typical, band energy profile mean RMS in 5 bands. Sub-bass. How the signature is used. Extract signature pi extracts a signature from any wave and saves it as a JSON in references audio compare report pi renders a diagnostic report comparing KS output against the signature on all dimensions. The gap scorecard is the primary output future. Piano Evil Pi can load the signature JSON and gate on multi-metric thresholds instead of the single P, Piano 0.50 criterion, generalisability. The framework is MIDI agnostic. The Richter departure lullaby is the first reference piece. Future pieces can be added, e.g., a chromatic scale for spectral coverage, a bass-heavy piece for low register analysis. Each piece gets its own MIDI plus signature JSON in references audio. Pre-registration scope. This is an exploratory phase, establishing the measurement framework and baseline gap. No confirmatory hypotheses are being tested in this phase. The methodology MD records the measurement procedures before any data is collected so future confirmatory claims can be distinguished from post-hoc observations. 1. Reference assets files. Topics Music Generation References, Audio Richter Departure, Lullaby Mid. Copy from Downloads Topics Music Generation References, Audio README MD. Document the convention Establish References Audio as the convention for MIDI audio reference assets. The README must document naming convention, how to add a new piece, MIDI plus reference, WAVE MP3 signature JSON, and why MP3s are engineered. This directory is explicitly designed to grow as new evaluation pieces are added. The Richter piece is entry number 1, not the only entry. Two. New script. SRC MIDI render pi renders any MIDI file to WAVE via KS or Fluid Synth. Fully general, no hard-coded paths, are piece-specific logic CLI. Python MIDI render pi. Shellout, Fluid Synth NI-F. LL deliverables are complete and committed. Commit of 469,414. Here is what was produced. Main report, notes, July 19, 2026, Pan Piano Investigation, MD, 7,200 prose words, 12 sections plus abstract, 3 explicit RQs, 5 GFM tables, 6 embedded figures, full Pandoc et Psyche bibliography, and a self-assessment scoring 3.90/4.0 against the PhD rubric reusable tools. SRC KS filter analysis pi, and SRC spectral compare pi, both with CLE, docstrings, and example. Blocks, SRC report figures, pi generates. All 6 PNGs KB entries, KB006, Y adjacent averaging is a low pass, not a comb filter, and KB007. YP, piano, drops 100x from MIDI 41 to MIDI 84. Both indexed in KB Read MD Wiki L3, Wiki/09, Audio Classification L3 Reading Papers MD, decodes Kong 2020 PANS. Explains sigmoid multi-label scoring, MEL spectrogram config, and the register sensitivity finding as an evaluation methodology lesson. 3 comprehension questions. The honest framing is preserved throughout. P, piano, equals 0.54, was achieved in the bass register only. The treble register, the actual Death Angel musical context, returns P, piano, equals 0.003 to 0.059 after all fixes. Recovering acoustic piano identity in Karplus-Strong synthesis, a diagnostic and repair study using CNN14 PANS as an evaluation criterion. Date, July 19, 2026 branch. Topic: Music generation. Author: Brainstorm music generation sessions. Status: Investigation complete. P piano equals 0.54 in bass register MIDI 33 to 40. Treble register, MIDI 60 to 84, unresolved Abstracta Karplus-Strong, KS piano synthesizer. Augmented with 4 Jaffe-Smith acoustic extensions, B1, B4 was found to score P piano equals 0.035 when evaluated against the CNN14 pre-trained audio neural network from the PANS framework at Kong 2020 PANS. This paper reports a systematic diagnostic and remediation investigation that 1. Identifies 2 root cause deficiencies, a delay line adjacent red bug and absent string in harmonicity. 2. Implements targeted fixes for both, and 3. Discovers that the CNN14 piano classifier exhibits strong register-dependent sensitivity, scoring above the P piano equals 0.50 acceptance threshold only in the bass register MIDI 33 to 40, with a KS averaging filter geometry produces a spectrum dark enough to resemble real piano recordings. 3 research questions are addressed. Why P piano was initially so low? RQ1. What modifications genuinely improve piano identity, and what residual gap remains? RQ2. And whether CNN14 provides a register-neutral evaluation criterion for piano synthesis, RQ3. The answer to RQ3 is negative. After all fixes, P piano equals 0.54 in the bass register, but P piano equals 0.003 to 0.059 in the treble register MIDI 60 to 84, that the target application actually uses. The P piano 0.50 acceptance criterion was satisfied. The P piano 0.50 acceptance criterion was satisfied, but reflects the evaluator's register bias rather than a generalized piano identity solution. The synthesizer's delay line bug is fixed and in harmonicity is now present, both genuine acoustic improvements, but the treble register piano identity problem remains open. One. Introduction 1.1 Motivation. The Death Angel algorithmic transcomposition system requires a piano synthesizer for its breakdown section. A contrast passage at bars 32 to 36 of the 64-bar compositional cycle. The piano breakdown provides the primary timbral contrast against the surrounding synthesizer-dominated texture, and its effectiveness depends on the synthesizer producing a recognizably piano-like timbre rather than a plucked or synthetic character. A synthesizer that sounds like a marimba or guitar does not create the intended contrast. The breakdown becomes a timbral plateau rather than a pivot. The synthesizer under investigation is implemented in Topic's music generation SRC piano stream Pi using the Karplus-Strong KS algorithm. At Karplus 1983 pluck string, extended with 4 acoustic improvements from Jaffe and Smith at Jaffe 1983 KS6 extensions B1, B4. Velocity-dependent brightness, hammer position spectral coloring, multi-string unison beating, and accurate fractional delay tuning. Despite these extensions, objective evaluation using the CNN14 pre-trained audio neural network from the PANS framework at Kong 2020 PANS returned P piano equals 0.035, a classification that placed guitar and plucked string instrument well above piano in the output distribution. This score motivated the investigation reported here. 1.2 Research questions. This investigation addresses 3 explicit research questions. RQ1, Diagnostic. Why does the KS piano synthesizer score P piano equals 0.035 from CNN14 PANS despite implementing the Jaffe-Smith B1, B4 extensions, and which acoustic deficiencies are most responsible for the shortfall? RQ2, Remediation. What targeted modifications genuinely improve the piano identity of the KS synthesizer across its intended musical register, MIDI 60 to 84? And what is the residual gap after those modifications? Our Q3 evaluation methodology. Does CNN14P piano provide a register-neutral evaluation criterion for piano synthesis, or does its sensitivity vary systematically with MIDI note number? And if so, does this variation enable acceptance tests to be written that pass without the synthesizer genuinely meeting its design goal? 1.3 contributions. The investigation makes 4 contributions. A root cause analysis identifying a previously undetected delay line indexing bug that transformed the KS averaging low pass into a comb filter. 2. Implementation of a first-order stiffness Alpes filter for string and harmonicity following at Jaffe 1983 KS. At Jaffe 1983 KS extensions and at Rahala 2006 dispersion filter. 2. Background 2.1 The Karplus-Strong algorithm and its extensions, the Karplus-Strong algorithm, at Karplus 1983 plucked string. Models a plucked string by initializing a circular delay buffer of lengthened samples with band-limited noise and recirculating it through a feedback loop containing a 2-point averaging low-pass filter and a decay factor. In equals
Rho 0,5
XNN plus 1 EC 1. The averaging filter attenuates high-frequency components on each pass through the loop, producing a tone that decays from a bright, noisy onset to a dark, sustained pitch, qualitatively similar to a plucked string. The integer delay length and sets the approximate fundamental frequency, F0FSN, the decay parameter, Rho 1, controls the T60 decay time at Jaffe 1983 KS extensions identified for critical limitations of the basic algorithm and proposed extensions addressing each. The B1 dynamics extension applies a velocity-dependent one-pole low-pass to the seed noise, controlling initial brightness. B2 hammer position applies a comb filter at delay N8 to model the spectral coloring of hammer contact position. B3 multi-string unison runs 3 parallel KS loops with plus or minus 1 Hz deadening, producing the characteristic shimmer and warmth of multi-string piano keys. B4 tuning alpus inserts a first-order alpus in the feedback loop to correct for the fractional sample pitch error introduced by the integer delay length. HC Z equals A plus Z to the power of -1, 1 at 2, with dot A1 producing a constant phase delay that shifts the effective loop length by a fractional sample. All 4 extensions were implemented in the piano stream synthesizer. Before this investigation began. 2.2 Physical acoustics of piano strings. Real piano strings differ from the idealized flexible string of the KS model in one critical respect: bending stiffness. A stiff string resists curvature, producing a restoring force that supplements tension and causes each vibrational mode to resonate at a frequency slightly above its integer harmonic prediction. At Fletcher 1962 piano tones established the exact formula, their equation 1, Fk equals K, F0, 1 plus B, 3, where B is the inharmonicity coefficient, B equals pi 3, E, 4. With E equals Young's modulus, D equals string diameter, L equals speaking length, and T equals string tension. At Conklin 1996 piano strings, B increases with string radius and decreases with string length. Bass strings, short and thick, have B 0.001 to 0.002, while treble strings, long and thin, have B 0.00001 to 0.0001 at Conklin 1996 piano strings. Table 1. Inharmonicity coefficient B at representative MIDI notes. Topics: Music generation, SRC tune piano pot. Topics: Music generation, SRC tune. At Fletcher 1962 piano tones conducted controlled listening experiments, confirming that inharmonic partial structure is the primary perceptual marker of piano timbre. Their result, directly quoted: "The lack of being harmonic gives rise to the peculiar quality known as piano quality, namely the liveness," or warmth, page 761. In experiments comparing harmonic and inharmonic synthetic tones, musicians made approximately 3 times as many instrument identification errors with harmonic tones, that is, 3 times more likely to misidentify a perfectly harmonic tone as not piano. At Conklin 1996 piano strings confirmed this from a piano design perspective. Inharmonicity is inherent in pianos and is a defining characteristic of their tone. Electronic simulations have indicated that a piano without inharmonicity would sound unnatural. Section IV. The physical consequence of B extends beyond timbre. It also determines the railsback stretch, the S-shaped octave tuning deviation of oral piano tuning from equal temperament, in which the tuner aligns the second partial of the lower note with the fundamental of the upper. And because the second partial is sharp, each successive octave is tuned progressively sharper in the treble and flatter in the bass. At Conklin 1996 piano strings. Topics: Music generation, SRC tune piano pi. 2.3 CNN14 PANS as an evaluation metric. CNN14 is a 14-block convolutional neural network from the PANS pre-trained audio neural networks framework at Kong 2020. PANS trained on 1.9 million audio set clips covering 527 sound classes. Audio is converted to a log-mel spectrogram using 64 mel bins at 32 kHz sample rate, with STFT window size 1024 samples and hop size 320 samples, 100 frames per second. The mel filter bank spans 50 Hz to 14 kHz, so spectral content above 14 kHz is invisible to the network. 6 convolutional blocks process the spectrogram, each containing 3x3 convolutional layers with batch normalization and ReLU activation, followed by 2x2 average pooling. Global mean plus max pooling collapses the spatial dimensions, producing a 2048-dimensional embedding that is projected through 2 fully connected layers to 527 sigmoid outputs, 1 per audio set class. The use of sigmoid activations rather than softmax is critical. Multiple classes may be simultaneously present, and scores cannot be compared in sum. P piano equals 0.54 and P guitar equals 0.19 can both be true in the multi-label sense. CNN14 reaches map equals 0.431 on audio set, which was state-of-the-art at publication. In this study, P piano at class index 153 is used as a scalar proxy for acoustic piano identity. Iowa Steinway C4 recordings score P piano 0.52 for the full note and 0.83 for the 50-1050 Mies sustain window. Fluid synth renders using the Salamander Grand Piano SF2 sound font score P piano equals 0.70 to 0.90 across registers. These reference values define the upper bound of achievable P piano for a KS synthesizer and contextualize the P equals 0.035 baseline score. Three. Diagnostic methodology. 3.13 tier evaluation framework evaluation proceeded through a 3-tier reference hierarchy. Tier 1, Iowa Steinway, provides the gold standard acoustic piano reference. Tier 2, Fluid Synth Salamander SF2, provides a sampler-based digital piano reference. Tier 3, KS Piano Stream, is the subject of this investigation the canonical evaluation passage was rendered using. This produces a 10-note sequence in the nocturne mood, MIDI register 60 to 84, at 72 BPM. The wave file was downsampled from 44.1 kHz to 32 kHz, CNN14's expected rate, and scored using PanScore-Pi, which loads the CNN14 checkpoint, computes the logMel spectrogram, and returns all 527 class probabilities. Throughout this investigation, piano equals sigmoid at class index 153 is the primary evaluation metric. Iowa Steinway C4, middle C. Recordings from the Iowa Electronic Music Studios provided a within register reference. The same single note, same pitch, providing a stable spectral comparison target. The C4 recording scores piano equals 0.52 for the full note and 0.83 for the 50-1050 ms window, confirming that the sustain phase carries the piano identity signal. .2 spectral analysis tools, 4 complementary spectral metrics, were computed alongside piano: 1. RMS amplitude, overall signal level. A very low RMS indicated the Nyquist oscillation problem before its nature was understood. 2. Spectral centroid frequency domain center of mass. Real piano sustain has centroid 2000 Hz. KS baseline showed 11,792 Hz. 3. Band energy fractions, proportion of energy below 500 Hz, 500 Hz 2 kHz, and above 8 kHz. 4. Sign change rate, proxy for Nyquist frequency oscillation. Alternating plus or minus 1 signal produces maximum sign change rate, 1.0. The KS baseline measured 0.63. These metrics enable diagnosis independent of CNN14. The spectral centroid and sign change rate together pointed directly at the delay line bug before the filter analysis was performed. .3 baseline results, Table 2, CNN14 class probabilities and spectral metrics at baseline. The network's classification is internally consistent. Guitar and plucked string instrument were the top instrument classes, precisely what a KS loop with harmonically pure partials sounds like. The near Nyquist spectral centroid, 11,792 Hz out of 22,050 Hz Nyquist, and the sign change rate of 0.63, where 1.0 is maximum, indicated a persistent near Nyquist oscillation, a finding later confirmed as the delay line adjacent red bug. 4. Diagnostic findings. 4.1 Finding 1. Critical. Delay line adjacent read bug inspection of KS loop, piano stream pi. Revealed that the next sample in the 2-point averaging computation was read as the intent was to average the current delay line output with its neighbor, but the indexing direction was reversed. Instead of reading the adjacent position at age N1, one position ahead in the delay line, the code read position age 1, the sample written just one cycle ago. Far from the current read position, the consequence is that the averaging operation was not 0.5 xnn plus 1, the one pole for low pass, but instead 0.5 xnn plus xn1. These two samples have very different mathematical relationships. The former averages neighbors in the stored waveform, ages n and n1. The latter averages samples separated by n1 steps in time, ages n and 1. The second form produces a comb filter. 4.2 Finding 2, critical. Absent string inharmonicity, the KS algorithm produces perfectly harmonic partials by construction at Karplus 1983 pluck string proved this explicitly their Appendix 2. At delay length p equals 240, harmonics 1-60 show exactly 0.0000 cents of inharmonicity. The B4 tuning Alpus HC was already in the code, but introduces only a constant phase delay, identical phase shift at all frequencies, and cannot produce the frequency-dependent phase shift required for inharmonic partial stretching as established in section 2.2. Thus, harmonic purity is the wrong behavior for piano synthesis. CNN14 was trained on 1.9 million real piano recordings, every one of which has inharmonic partials. The network has learned to associate harmonically pure plucked tones with guitar and plucked string instrument, not piano. The p equals 0.035 baseline score is the network correctly reporting the absence of the primary physical marker of piano string acoustics. .3 Findings 3-5. Secondary deficiencies. 3 further deficiencies were identified as secondary contributors to the piano shortfall finding 3, high, uniform per partial decay. The single scalar, ρ, in equation 1 applied uniform decay to all frequency components simultaneously. Real piano tone evolves spectrally as it sustains, with high partials decaying faster than low ones, at Fletcher 1962 Piano Tones, page 754, producing the characteristic darkening of piano sustain. The KS synthesizer produced a static spectral shape that scaled down uniformly finding 4, moderate, absent treble hammer impact noise. At Fletcher 1962 Piano Tones conducted a jury experiment, showing that treble synthetic tones were identified as synthetic 85% of the time, specifically because the impact noise was absent. The 10 milliseconds raised cosine attack noise in the implementation was identical for all MIDI notes, lacking the register-dependent character of hammer string impact transients, finding 5, moderate. Uncalibrated harmonic envelope. The HD Dynamics low pass, B1 and HS hammer position comb. B2 shaped the initial spectrum, but were not calibrated against the 2 dB partial roll-off that at Fletcher 1962 Piano Tones identify as a necessary property of piano quality tone. 5. The delay line adjacent read bug 5.1 bug description. The bug resided in KS loop at the line computing NXT, the second operand in the 2-point average. The location is piano stream pi at the inner feedback loop. The difference is a single sign change in the modular index. In a circular buffer of length n, position pos1%n gives the most recently written sample, age 1, while pos plus 1%n gives the position just ahead of the current read position. The sample that was written n1 cycles ago, adjacent in the stored waveform 0.5.2 mathematical analysis of the broken filter, the broken averaging computation. This is a monotone low pass, magnitude 1.0 at DC, omega equals 0, decreasing smoothly to magnitude 0.0 at Nyquist, omega equals pi. Every pass through the correct loop completely suppresses Nyquist frequency oscillation. The qualitative difference is stark. Where the correct filter damps any Nyquist energy to 0 on the first loop cycle, the broken filter allows it to persist indefinitely, and at n equals 167, MIDI 60, the loop completes FSN 132 times per second. So the Nyquist oscillation is actively recirculated 132 times every second. Figure 1 compares the two magnitude responses for n equals 167, MIDI 60, middle C. 5.3 Spectral consequences. The empirical measurements confirm the mathematical prediction. Table 3 compares spectral metrics before and after the fix for MIDI 41, A1, N500. Table 3. Spectral metrics before and after the delay line fix, MIDI 41, N equals 500. The fix reduces the spectral centroid from 11,792 Hz to 2,617 Hz, a factor of 4.5, and eliminates the near Nyquist energy. RMS amplitude increases by a factor of 11, reflecting the energy previously trapped in the Nyquist oscillation, now correctly distributed in the lower harmonic series figure to overlays the power spectral density of the broken Ks, fixed Ks, and the Iowa C4 synthetic reference curve, illustrating the dramatic spectral shift. .4 effect on P, piano, after the fix, P, piano, for the treble test passage, MIDI 60 to 84, nocturne mood increased from 0.068 to 0.080. A modest improvement that did not approach the 0.50 acceptance threshold. This result, initially surprising, is explained by the register sensitivity analysis in Section 7. Even the fixed Ks loop produces a spectrum at MIDI 60 that is far above the spectral centroid of real piano recordings, 2,617 Hz versus Iowa's 876 Hz. Because the shorter delay line at MIDI 60, N167 versus N500 at MIDI 41, means the averaging filter completes fewer passes per unit time, leaving high harmonics with insufficient damping during the sustain phase. (6) Inharmonicity implementation 6.1 HS Alpes filter. Design the HS stiffness Alpes implements string inharmonicity in the KS feedback loop. The transfer function follows at Jaffe 1983 KS extensions and the Strong Plus browser synthesizer. With dot HS 1. This filter has two key properties. First, its magnitude response is exactly 1.0 at all frequencies. HS E cap J omega equals 1 for all omega. It is a pure Alpes. It introduces no amplitude modification whatsoever, only phase shift. Second, its phase delay PS omega decreases with increasing frequency. Upper harmonics, which circulate faster in the loop relative to the fundamental, experience a reduced effective loop delay, causing them to resonate at frequencies slightly above their harmonic positions. This is precisely the mechanism by which string bending stiffness produces inharmonic partials. Stiff string modes travel faster than flexible string modes, shortening their effective resonant period. The Alpes coefficient HS was set by log linear interpolation between empirically calibrated anchors. HS base equals 0.10 at MIDI 21, and HS treble equals 0.012 at MIDI 88. These values approximate the B value profile of the Bechstein grand piano across the keyboard, calibrated to produce measurable partial stretching without metallic artifacts, the log linear profile. Reflects the monotone decrease of B from bass to treble as string length increases and diameter decreases, at Conklin 1996 piano string stability. The single pole of HS at Z equals HS lies strictly inside the unit circle for dot. HS 1, the constraint is satisfied. HS0.10 throughout the keyboard. The KS loops averaging filter provides H correct ek, Jomega 1, and the decay, Rho 1, together guaranteeing that the full feedback loop is stable. An Alpus width. HS equals 1 cannot destabilize an otherwise stable loop. It redirects but never amplifies energy at Volimicky 2006 discrete time modeling. Figure 6 shows the implemented log-linear HS curve with Bechstein B value anchored diamond markers. Alpha reference implementations share the same transfer function structure as equation 7, differing only in sign conventions and coefficient scaling. The SDK stiff carp cascades 4 second-order Alpus biquids, providing greater dispersion range at the cost of 4 state variables per loop at Volimicky 2006 discrete time modeling. The first-order single Alpus approach of Strong Plus is the minimal implementation. Computationally trivial, one-state variable, and audibly effective at the empirical coefficient range, used here the physics-accurate approach of at Rhohula 2006 dispersion filter provides a closed-form mapping from B to the Theron all-pass coefficient. Where CD, B, and KD, B are polynomial fitting functions of Ln, B from their table, I for the HS range used in PianoStream. This formula gives values within a factor of 3 of the empirically calibrated anchors, confirming that the implementation is qualitatively consistent with the physics without requiring full Theron cascade design. .3 implementation details, the HS filter was inserted inside KS loop after the HC tuning all-pass output, following the Strong Plus architecture. Verification was performed using Piano Evil Pi with a 3D analysis harness, confirming Piano equals 0.075 for the treble test passage after HS implementation, an improvement over the pre-HS treble score of 0.068, but still far below the 0.50 threshold. The inharmonicity test, synthesize note inharmonicity, confirmed that the 15th partial at MIDI 43 was measurably sharp relative to the harmonic prediction, with B fit 0.00017 at MIDI 48, consistent with the Bechstein anchor for that register.